Can I start? But good evening. So good evening and welcome to the book. We can share also. 11th lecture of Advanced NMR Spectroscopy course. For the last 10 lectures, we have been discussing about different aspects of solid state NMR. So we started with why is solid state NMR, why not solution NMR, what are the advantages of going for solid state NMR, and what are the parameters which we can get from solid state NMR. All those things we were discussing. So now, so basically this class I have made in such a way that lectures I have made in such a way that I have giving more examples so that you will get a feel of the samples or feel of the utility of NMR, solid state NMR for understanding the structure. So I am not at all going about anything regarding the theory of the NMR or theory of the pulsed solid state NMR, etc. So I am just basically it is like a basic course only. It is like a basic foundation course to solid state NMR. That is why I'm giving many times I'm giving so that I'm giving examples. So another thing is that try to solve the problems which are mentioned in the assignment. If possible, submit by next week, next Monday, maybe next Monday our last class, 12th lecture. We will see if required. I think I will try to wind up with into 12 lectures. So we have been discussing about different aspects like dipole-dipole interaction, chemical shift anisotropy, then how somebody has right, how we can use this type of interactions to get structural information from solids. So this aspect we have discussed in the last class very well. So last class we discussed about DQ-NMR. You know, DQ-NMR is nothing but double quantum NMR. So double quantum NMR one axis, single quantum NMR another axis, you get a very good information. You get more information, means you, whatever information which is hidden in one dimensional NMR, we can get it by recording a two-dimensional NMR. You can talk about the medium range order in inorganic compounds. All these things we have discussed. Just I am telling this to refresh your memory. Then we have also discussed, we have got a correlation like Cauchy spectrum which you record in heteronuclear correlation or homonuclear correlation you record in solutions. We can also have a correlation spectrum using 2 carbon-13.
Shivangi has joined, no? Shivangi was
Yes.
joined already?
Yes.
So message came.
Shivangi. So these things we were discussing yesterday last class, and I hope you understood. In case any problem, you please mail to me or you call me at any time. So toward the end of the last lecture, we discussed something called a spin echo experiment. Correct now? What is this spin echo experiment? Initially, it was started to avoid the dead time problems because the detector now it is very difficult to get signal at zero time, because there will be always some time lag will be there because electronics cannot detect what is the signal at zero time. So some information sometimes you get lost or you may not get because of this. You lose that information, and to prevent that only we do this type of experiment. So this we have already discussed also in the last class. So echo will be like that. So echo is something which has gone, means the signal has come which is decaying because of the inhomogeneities. By applying a pulse, you again refocusing it. The defocusing is taking place, and the defocusing is converted to refocusing, and we get a refocused signal that we call as the echo. So this also we have discussed at least to a certain extent in the last class. Now let us discuss in detail what is a spin echo experiment, which already we have defined or we have explained, and then how it can be used for understanding the structural information. So the same thing I am showing here once again to refresh your memory. See, I have got a 90-degree pulse. Now, pulses 90-degree means it's a very simple concept only. You shift the magnetization to exactly 90-degree with respect to the applied field. That is why we call it as a 90-degree pulse. I have not explained in previous classes what is a 90-degree pulse. I thought you must be understanding or you must be knowing because you have already understood you have attended solution NMR class. So it won't be a difficult. So if you apply a 90-degree pulse, in fact, a pulse width will be different in solution and solid state. There are experiments to calculate what is the pulse width for 90-degree and what is the pulse width for 180-degree, etc. These are simple experiments are available. Very simple experiment in which you measure the intensity as a function of pulse duration, and whichever pulse giving the maximum intensity, we give us a 90-degree pulse, because normally the detector is mutually perpendicular to the carrier wave frequency axis as well as the applied magnetic field. So if you have an Z, if you consider as the axis for the magnetic field, static magnetic field, and if you apply 90-degree pulse along X axis, then your signal will be coming in the Y axis. Correct, na? So that much, I think probably all these things you must be knowing. This can be considered if you consider the vectorial nature of magnetic moments or magnetic vectors. So now I am doing after applying a pi by 2 90-degree pulse now, I am applying a 180-degree pulse again on the x-axis. So if I am applying an 180-degree pulse on the x-axis, the magnetization also will turn 180-degree. You see here, the magnetization which has started spreading has moved 180-degree away, and you start getting refocusing in the opposite direction. Is it not? And after some time it will refocus. So this is also a echo only, because in the previous case we have shown the after 90-degree pulse along the y-axis, we apply 190-degree pulse along the x-axis. You see x direction I have applied. So that is where the change in direction is there. So initially we apply on y-axis and then followed by x-axis. But here the change is nothing but here both the pulses are applied along the x-axis. You see here 190 degrees on x-axis, that is why pi by 2x, and 180-degree pulse also on x-axis. So then after some time it undergoes refocusing. Say defocused magnetic moments or the magnetic vectors will undergo refocusing after some time. So that is what happening here. That refocused signal we call as an echo signal. So obviously, if t is the time in which you apply 180-degree pulse, and after another t, means after 2t, you get the signal. So that is why magnetization as a function of 2t I have written here. So for the time being, you need not buy hard or etc. Just see that there is a change in magnetization as a function of time. Now, how this we can utilize for understanding the internuclear distance? That is what I am going to tell in the next 2 to 3 slides. How the spin echo can be utilized for understanding the structural information. So you see this pulse program just written as I. Let us say I is a pulse program. I apply a pulse along the y-axis, correct na? Pi by 2 pulse. Then after some time, we apply a 180-degree pulse, which is slightly, that is why I am telling the pulse width is higher, and what you get is nothing but a echo here. That is what I have written as AQ. Okay. Now I am doing one more thing. See, I can be coupled with S. For example, if you take I as proton, S can be considered as carbon 13. Is it not? So if you consider I as proton, S can be considered as a carbon 13. Now what you are doing in the S channel, or which is nothing but the carbon 13 channel, you are applying a 180-degree pulse. So what will happen? The spins of S will get inverted, or it will undergo change by 180-degree. As a result of this, what will happen? Whatever dipole-dipole coupling is there between I and S get affected because of this pi pulse applied to the S channel. Is it clear to you? What I was telling is that I am doing an echo experiment with I nucleus, which is, let us say, it is proton. Now I could have done the experiment and completed to take into consideration of the dead time problems. I could have finished the experiment, but rather than doing that, I am doing one more pulse sequence in which I am applying the S channel, which is nothing but the carbon 13, a 180-degree pulse. I and S are dipole coupled because we are doing the experiment in a static mode. Forget about, for the time being, the magic angle spinning. We are doing the experiment without spinning the sample. So without spinning the sample, always there will be a dipole-dipole coupling. Is it not? Because we always discussed in all previous classes that the magic angle spinning averages the dipole-dipole interaction because of the which dependent? 3 cos squared theta minus 1 dependence. The dipolar Hamiltonian is having an angular dependence of 3 cos squared theta minus 1, and once theta becomes 54.74 degree, which is nothing but the magic angle, you get the averaging of dipole-dipole interaction. But here we are doing static mode, so dipole-dipole interaction is not getting averaged out. But instead of doing a simple echo, I did one more thing, that I applied a 180-degree pulse and I disturbed the population or the magnetization of the S vector or S nucleus. So what happens, since there is a dipole-dipole coupling, the echo which is seen at this point, AQ, gets affected. Suppose you see the blue, you say as I, and S is, let us say, green. Now you, by applying a 180-degree pulse, you are changing the orientation of the vector. Correct, na? If you change this as S and if you consider this as I, if you change the orientation, for example, here what happened, the green color, instead of aligning in a particular direction, you have changed the orientation. So due to this, the echo intensity which we see at acquisition or AQ gets affected. So echo intensity, in other words, technically we say the echo intensity gets modulated because of the 180-degree pulse applied at the S nucleus channel. Of course, you can apply it as a function of time. Here we have applied at a time 2/3 of tau, where tau is nothing, 2 tau is nothing but the acquisition is complete at this point. So you can vary this time, that is called T1. By varying T1, you can generate the echo signal. So echo signal can be generated as a function of time. Is it not? So echo signal you are generating as a function of time, and from the decay curve, you get a decay. Correct, na? You get a decay, sometimes you get a build up, all those things. So let us discuss that. So echo time you are affecting, or echo time you are measuring as a function of time, or echo signal intensity. So from this, you can get information regarding dipole-dipole interaction. So once you know the dipole-dipole interaction, then what will happen? We can generate distance between the groups involved. So this is the main purpose of doing a spin echo double resonance experiment, SEDO. I thought I will give you an example with a sample. Correct, na? Once I give a sample, then if you do a SEDO experiment, what information you can get can be understood. That is why normally, as I mentioned earlier, I always give the NMR spectra of samples so that you can view, or you can understand, or you can visualize how or what type of information can be obtained from this type of studies. Let us move further. So again, I think I am showing the same thing only. I am showing the pulse sequence. And here what we are going to do now, I am trying to understand the distance between aluminium. Sorry, I made a mistake here. Instead of aluminium, I have written A1. So it is aluminium. Sorry, kindly consider this is aluminium. 27 AL. 27 AL. So this is 27 AL, phosphorus 31. Distance I want to evaluate in aluminophosphates. See, aluminophosphate, now there are many types of aluminophosphate. There are many commercially available aluminophosphate, like aluminophosphate 5, aluminophosphate 21, aluminophosphate 11, etc. These are all called molecular sieves. These molecular sieves now are having lot of pores inside. And these pores can absorb gases like carbon dioxide, sometimes nitrogen dioxide, nitric oxides, etc. So a lot of people work on this type of molecular sieves. So many times these molecular sieves also have application in vacuum technology, etc. Probably we will read, or you might be knowing all these things. So let us try to understand how to evaluate aluminium to phosphorus 31 in aluminophosphate by a technique called SEDO. What is SEDO? SEDO is nothing but spin echo double resonance. These are all called double resonance. Why double resonance? Because two nuclei we are simultaneously probing. Aluminium also probing, phosphorus 31 also probing. Not single resonance. These are all called double resonance, and since spin echo is involved, we call it as a spin echo double resonance. This is a very, very old paper which I am showing it here. Some few, I think almost like 30 years back, this technique was established. Of course, pulse modifications have been done to improve the signal noise ratio. So here we are applying the echo pulse on aluminium 27 nucleus. We are monitoring the echo of aluminium, and we are applying a dephasing pulse. Pi pulse, we call it as a dephasing pulse because it changes the phase. It dephases the pulse. So that is why we call this as a dephasing pulse. A dephasing pulse is applied on P31 nucleus. Okay, this is what we are doing. And next I have asked a question, why not the other way? So let us discuss it a little bit later. Maybe after 2-3 slides, we will discuss that aspect, why we are not doing the other way. But let us continue like that. like this, the echo pulse is supplied on the aluminum-27 and the dephasing pulse is supplied on the phosphorus-31 nucleus. Let us move further. Another extra, so this is a pulse program I have done. Then what are the other things which we are doing? Experiment is done in static mode. Correct, na? So I am telling that there is no spinning. So dipole-dipole interaction is not getting averaged out. Then another is what? Echo pulse is supplied along the I nucleus. That also just now I have mentioned. And dephasing is supplied to the S nucleus. So dipole-dipole coupling and CSA. CSA means what? Chemical shift anisotropy. They get refocused. Why? They will not get defocused because we are applying a 180-degree pulse. This 180-degree pulse main job is to refocus the anisotropic interactions such as chemical shift and also the interaction like dipole-dipole coupling. Another one is the dipolar coupling sign of S get inverted and this results in the reduction or perturbation of the dipolar coupling. You understood now? The moment I apply a 180-degree pulse, what happened? The S spin, the orientation changes. You see the orientation change of, let us say this is S spin, the S spin orientation has changed. So the dipole-dipole coupling get modulated or dipole coupling gets affected, or it can say it can decrease because the orientation has changed. So echo intensity should decrease. Correct. Now signal intensity must be lost. You should lose the signal intensity. Why? Because the orientation has changed. Dipole-dipole interaction is no longer there. So the decrease in intensity, the decrease in the intensity of echo is nothing but it is related to the IS coupling. Correct? Na? So let us move further. So let us take a typical example of an aluminium phosphate. Aluminium phosphate is a molecular C. So here aluminium is tetrahedrally coordinated and phosphorus is what? Phosphorus is also tetrahedrally coordinated. So aluminium 3 plus and phosphorus H3PO4 means PO4 3 minus. They form a neutral compound and AlPO4 and PO4 form a corner shaded tetrahedra, and they share it in such a way that you generate at least multiple type of pores. For example, this is a big pore, this is a small pore, this is a medium pore, and this is a small pore. So what information I am getting by doing a SADOR is nothing but I get the dipole-dipole interaction between aluminum and phosphorus. Believe me, this aluminum phosphate is having only one type of aluminum and only one type of phosphorus. Crystallographically, there is only one type of phosphorus and only one type of aluminum. Aluminum in crystallographically only one side, aluminum one side and phosphorus one side. There is no multiple phosphorus environment and there is no multiple aluminum environment. So if you do a magic angle spinning NMR, what we get is a very single signal for 31P and we also get a single signal for 27AR. So there is no multiple phosphorus, which is only one type of phosphorus and only one type of aluminum. So the whatever the distance or the whatever dipole-dipole coupling you get or the distance you evaluate from the dipole-dipole coupling is nothing but the average distance between aluminum nuclei and phosphorus nuclei. Let us see how it is calculated, how you can get this information. So there is something called SADOR fraction. What is SADOR? SADOR is nothing but spin echo double resonance. What is a SADOR fraction? SADOR fraction can be expressed by this value. So this can be experimentally determined. How you can determine experimentally? Because there is a signal called S0. S0 is the aluminum 27 echo is intensity without any 31P pi pulse. Go to the pulse program. See, if I don't apply any pi pulse, let us say I am not applying any pi pulse, then what is the intensity? That is called S0. Correct? That is called S0. That is nothing but the echo. Spin S stands for spin echo intensity at 0 time. 0 time means you don't have any 31P pi pulse. And T1 is nothing but the echo intensity with a pi pulse, 31P pi pulse at a time T1. You see here T1 is applied here. After some time only you are applying pi pulse for the P31 channel. So there is a time delay involved, T1. So by varying T1, you can apply the pi pulse at a different position. So you can easily calculate the SADOR fraction. S0 we know without any pi pulse, and T1 is nothing but the intensity of the echo signal after applying a pi pulse at a particular time called a T1. Is it? So this SADOR fraction you are getting. Okay, and this SADOR fraction you can plot as a function of T1. correct, as a function of T1. So in principle, you should see, what? You should see a change, correct? So S0 is nothing but a signal intensity without any pi pulse, and ST1 is the aluminum echo intensity with a 31p pi pulse. So this is nothing but an experimental parameter. Now what happens? If you know the distance vector, and if you know how it is oriented with respect to the angle of the applied magnetic field, you can theoretically also calculate ST1 by this expression. Of course, you have to go to polar coordinates, and Sador curves can be generated theoretically. So Sador curve can be generated theoretically by using this type of expression. No need to remember all those things, just to get a feeling of how to generate theoretically the Sador curves only I have shown here. So yes, rho is nothing but a function of dipole-dipole coupling, and the T1. T1, you know, is nothing but the time delay involved in the application of the pi pulse. The product of D into T1 is called a rho. So the spin echo intensity as a function of rho, you can calculate by this expression, alpha, theta, phi, etc., rho, etc. It is coming from the polar angles, and from this angle you can calculate. If you know the principal axis system as well as the symmetry of the molecule, etc., you can calculate and get the value of S and rho. Correct? So this is nothing but the Sador intensity calculator. And if you calculate the Sador intensity and multiply with the scale factor, what you generate is nothing but the experimentally observed Sador. So the scale factor is related to the dipole-dipole coupling constant, which is expressed by this relation. So from this gamma I and gamma S is a literature value, you know, it's a zero-magnetic ratio. So if you know all these values, you can get distance between gamma I and gamma, means I and S. I is nothing but, let us say, proton, S is nothing but C13, then you can get the value of IS, but here it is, I is nothing but observable nucleus aluminium, and S is phosphorus, so you can get the distance between aluminium and phosphorus by this technique. So what exactly you have to remember is, we experimentally evaluate spin echo intensity, and then you can also theoretically evaluate, then you multiply the theoretically evaluated Sador as a function of time with a scale factor and match it with that of the Sador experimentally you are getting. So this scale factor is nothing but the dipole-dipole coupling. From this you can evaluate the coupling constant value. So T1 microsecond, this is the value observed. If you see here, this is the whatever you are the squares are nothing but the experimental data as a function of time we have put. As a function of time, you keep on changing the Sador intensity, spin echo intensity after applying the pi pulse. So whatever this square is nothing but the experimental, and the experimental curves have been fitted with a straight line. That is what you are seeing here, and the value corresponding, I have made a mistake, you have to, because this arrow corresponding to this value, this continuous line. I think I have to pull it. I think now I may not be able to pull it, but please consider that this arrow points to this continuous.
With the pen,
pin with the pen I can show actually. I think while making. Yeah. I am sorry that I could not draw it, but
that's okay.
Yeah. So this continuous line is a fit of the experimental data, and from that you get a D value. D value, you know how to calculate? I can calculate by theoretically, and I can know the experiment, and if you the scaling factor, that is nothing but the D, and once you get the D value, you can calculate the aluminium phosphorus average distance, and aluminium phosphate average distance turns out to be around 3.15 angstrom. And what will happen if the D value, if the distance is higher? So you can back calculate it, correct? Now you can back calculate, and that is why if the distance is nothing but 3.25 angstrom, then you will get this curve. And if the distance is 3.05 angstrom, you will get this curve. So what I want to show is, with respect to the variation in the distance between aluminium and phosphorus, you can vary the value of D. Or the spin echo experiment can be very well used to understand the distance between the aluminium and phosphorus. So this is what the message conveyed through here is, that you can evaluate the distance between aluminium and phosphorus or any dipole coupled nucleus by doing a Sador experiment. Sador is nothing but spin echo double resonance. So as I mentioned, here we have done the experiment by applying echo pulse on aluminium 27 and dephasing pulse on phosphorus 31. Then why we are applying, why don't we do the other thing, reverse? Echo pulse on phosphorus 31 and dephasing pulse on aluminium 27. That also can be done. I don't think there is any problem. But the main difficulty we may face is that aluminium, what happened is a quadrupolar nucleus. Aluminium is called a quadrupolar nucleus. What is quadrupolar nucleus? We will discuss probably to the end this class, or maybe in the last lecture we will discuss, or maybe after that, if required, we will discuss. Aluminium 27 is having a spin value of 5 by 2. Nuclear spin is 5 by 2, whereas phosphorus 31 is having a nuclear spin of half. So advantage of half spherical nucleus with a spin half is that the charge distribution is uniform. If you take a phosphorus 31 nucleus, it is having a spin of half and its charge distribution is neutral, and so nonlinear effect due to this charge distribution, inhomogeneous charge distribution will not be there. Whereas aluminium 27, its distribution or the charge distribution in the nucleus is asymmetric. So that is why we see sometimes whatever, if you apply a pi pulse now, all the magnetization curves will not turn by 180 degree. So that because of the inhomogeneity in the inhomogeneity in the nuclear properties, you can say, or because of the quadrupole coupling constant, or asymmetry in the environment, or asymmetry in the charge distribution in the nucleus, etc. So that is why generally, if you want to do a dephasing pulse, you apply on spin half nucleus so that we can completely defocus it or dephase it. Because this dephasing is an important aspect. If you don't dephase it, we will not get we will not be able to calculate the spin dipole coupling constant value. So let us move further. So hope you understood how to evaluate the spin echo intensity in a double resonance experiment and how to correlate with the D value. D value is nothing but the scale factor, and it is related to the dipole coupling constant, and from that you can calculate the distance. And this value, in fact, if you see now, it matches the average aluminium phosphorus distance, matches well with that of the X-ray diffraction studies, the results obtained from the X-ray diffraction studies. So in the previous case, I have discussed a molecule called aluminium phosphate 5. It's a molecular sieve in which aluminium is tetrahedra, phosphorus is again tetrahedra. There is only one type of phosphorus and only one type of aluminium. I have written here, only one type of aluminium and only one type of phosphorus. So whatever interaction is taking place is between the aluminium of one type and aluminium of another type. But in aluminosilicophosphate, there is a compound called aluminosilicophosphate, silico-aluminium phosphate, and short form it is called SAPO. SAPO is also a molecular sieve, very widely used for absorption of gases and separation of inert gases, etc. SAPO 11. This 11 and Alna is a commercial name, like ALPO5 is a commercial name. Probably you might have heard another compound called MCM41. MCM41, that 41 stands for the commercial, now MCM also stands for the commercial brand or commercial product. Similarly, 11 also coming from that commercial product only, a number given by the company. So here what happened? Here we have AlO4 tetrahedra, we have PO4 tetrahedra, and we have also SiO4 tetrahedra. I think I have not written silicon, that is why somehow it is not. We have got an SiO4 tetrahedra. So we have SiO4 tetrahedra, all are corner shaded. I have not found the structure, but consider that SiO4 tetrahedra is there, they are all corner shaded. Again, we have like this type of structure. We are having a porous structure, and this can be used for monitoring the for absorbing gases, and also we can do SEDOR experiment to find out the average distance. So here also you see aluminium phosphate distances are coming around 3.17 angstrom only. So the value is coming around 400 plus or minus 20 hertz. Normally the dipole coupling constants are expressed in terms of heads frequency. So from that you can calculate the ALP distance. So just for a feeling of what information it gives and how it matches with the XRD or neutron diffraction. Normally to find the bond length, bond angle, or bond distances, what we use is again a diffraction technique, correct? Na? Either we use a neutron diffraction technique or either use an XRD, X-ray diffraction technique. Whereas it is better to compare the values you get by spin echo double resonance as well as XRD and neutron. You can see the values are very close. In the case of aluminium phosphate, you see 3.15 and 3.14. SaPO4, which is nothing but silicon aluminium phosphate 11, which is nothing but the value is very close. Slightly SADOR is giving a slightly higher value compared to the XRD value. These are maybe something maybe to do with the error limits also. So you can always say the comparable values can be obtained by a SADOR experiment as well as diffraction experiment. That is what I want to convey from here. See, for your understanding or for explaining purpose, I have taken a simple system like aluminium phosphate, silicon aluminium phosphate, etc., where there is only one type of phosphorus, only one type of silicon, and only one type of aluminium. But many times we may not get like that. We may have a variety of phosphorus. We may have a variety of aluminium. So in such cases, SADOR technique have some problem because we may not be able to accurately say or accurately evaluate the distance between the phosphorus and aluminium atom. And also the whatever value you get by SADOR experiment, you cannot correlate the distance, from which distance to which atom to which atom, you may not be able to say. So for that only a modification has been done in the SADOR experiment, that is called a radar. Radar is nothing but rotational echo double resonance. We were using SADOR because SADOR is having a problem, inherent problem. To circumvent that, people have gone for a technique called a radar. Radar is nothing but rotational echo double resonance. In a normal language or in a common language, we can say it is a mass equivalent of SADOR. What is mass equivalent? Mass is nothing but magic angle spinning. So if you do, in all SADOR experiments, we do static experiment. We don't spin the sample. At static condition, without spinning the sample, we do the experiment. When you do experiment under magic angle spinning, then we call it as a radar. Hope it is clear. Let us discuss what radar gives now. So I have discussed, okay. The radar answers many of the problems with respect to the multiple sites, multiple environments around phosphorus and aluminium. So before going for radar, just one point I missed, I thought I will indicate you because I told now here also SaPO11 we have got silicon, we have got aluminium SiO4, we have got PO4, we have got aluminium AlO4. Here we can do two types of SADOR experiment. One is aluminium you can apply as a echo and phosphorus you can apply as a dephasing. Alternatively, aluminium you can keep it as an echo and silicon channel you can use it for dephasing. Or you can use silicon channel as an echo observation for monitoring the echo and phosphorus channel for applying the decoupling or dephasing. So this type of variation can be done. Accordingly, you get the distance between silicon phosphorus or aluminium phosphorus or phosphorus aluminium, etc. And one more point is that you can suppose the value you get when you take phosphorus as echo observation and aluminium as dephasing pulse, or aluminium as echo observation and phosphorus channel for the dephasing pulse, the value will be nearly same. There won't be much error. So you can also do that experiment and also confirm what is the average distance between phosphorus and aluminium in such systems. Hope things are clear to you. In case you have any problem, please raise your hand or you give a signal. So hope this also you understood. Now suppose you take another aluminium phosphate. There is an commercial aluminium phosphate called aluminium phosphate 21. So previously we were discussing about aluminium phosphate 5. Correct? Now aluminium phosphate 5. Sorry, I think it is something hiding here. I will just remove it here. Aluminium phosphate 5. Previously we were discussing. Now we are discussing something called aluminium phosphate 21. Just a moment. Now we are discussing a compound called aluminium phosphate 21, APO421. You see here, the moment I record a P31 NMR, in the previous case I got only one signal, only one type of phosphorus. Whereas in this case, you see multiple signals, 3 signals you are seeing. One is at chemical shift minus 133.3 ppm, another, minus 13.3 ppm, another is at minus 21.1 ppm, and another is at minus 30.3 ppm. This is just a single one-dimensional NMR, single pulse NMR. If I do a single pulse NMR, or if you do a spin, just okay, a spin echo, not a SADOR, if you do a spin echo experiment, then what you get is 3 signals you get, one-dimensional NMR. That means what? 3 phosphoruses are there. Once 3 phosphoruses are there, you may find it difficult if you do a Sador experiment, because it will give the average picture. Which distance corresponding to which the phosphorus we may not be able to say. So I have just, for your understanding, I have written here the signal at minus 13.3 ppm corresponding to a phosphorus oxygen Al bond angle of 137.4, whereas 21.1 142 and minus 30.3 correspond to 148 degree. So you may think why the chemical shift decreases. You see, chemical shift is become minus 13, minus 21 and minus 30. It means systematically getting shielded. Phosphorus atom is getting shielded and the bond angle increases. What is the reason for this? Why? Probably this we have discussed also in the case of silicon aluminum silicate, aluminosilicates also. The same explanation is valid here. In the case of aluminosilicate, we told, what we have told? See, as the bond angle increases, once the bond angle increases to higher and higher value, the S value around oxygen, the hybridization or the S character of the oxygen orbital decreases. Is it not? Because in water it is sp3 hybridized. So S, which is one, let us say roughly around 109 degree. So what is the sp3 hybridization? S character is around if you say sp3 4 around 25%. But as you increase sp3 become sp2 and sp, the S bond character of the oxygen increases. So oxygen pushes the electrons toward phosphorus, and as a result of this, we see a shielding around phosphorus. That is why with increase in bond angle 137 to 142 to 148, we see a systematic increase in shielding or systematic decrease in the chemical shift value. So that is for you to understand this only I have given these values. So remember that the shielding around phosphorus increases with increase in the bond angle POAL linkages. So there are 3 different types of phosphorus, and if you do a Sador experiment, what you get is an average picture. So for that only we move to a technique called the double resonance, spin echo double resonance. Rotational echo double resonance. And in rotational echo double resonance, the principle is same. Only thing is we are doing a magic angle spinning. We also spin the sample. In Sador, we do experiment in the static mode, and in radar, we do by spinning the sample. Let us see what are the things which I have written here. See, I have written here carbon 13. Carbon 13 spin echo you are observing. Correct? Na? That is acquisition means you are observing the spin echo of carbon 13. So same only I am applying a 90 degree pulse, I am applying a 180 degree pulse to generate echo, and you get acquisition time. Correct? Na? Acquisition means you are recording the echo signal. So the first part is very clear. Is it not? Because first part is same as that whatever we have done in Sador. Is in Sador also same thing we did, na? Echo pulse we applied, and after some time we applied a 180 degree pulse and we measured the echo. But here, what happened? Here, in addition to applying 180 degree pulse, we rotate the sample also. You see here in A experiment, only we are measuring the spin echo. That is what clear. See, I am applying a 90 degree pulse around the y-axis, and again a 180 degree pulse around the x-axis. I get an echo and I measure the echo. Now, what happened then? I am applying 2 pulses. Rotor synchronized pulses I am applying. I apply the 180 degree pulse with synchronizing with respect to the rotor frequency, and then this is the H1 channel, this is carbon 13 channel, and this is the proton channel. Proton channel I apply 180 degree pulse. In between the one rotor period. TR is nothing but the rotor period, correct? Na? You know what is rotor? Rotor means something but we fill the sample. I have shown you the photographs of rotor, in which you can see how to fill the samples and how sample is spun. So once a complete rotation takes place, one TR will be over. Correct? Na? So that is why TR is nothing but, once you know the frequency, 1 by frequency is nothing but the rotational period or the rotational time. So you apply 2 180 degree pulses. What they do? 180 degree pulses, I don't know whether you understood in previous classes or not. They recoupled. They do dephasing also, but they recouple also. They recouple the dipole-dipole interaction. Why we need to recouple? Because you are doing spinning the sample. You are doing a magic angle spinning. While doing magic angle spinning, what happened? The bond vectors can random orient at an angle of 54.74 degree, and the dipole-dipole interactions can get averaged out. So to prevent the dipole-dipole interaction getting averaged out, we apply a rotor synchronized 180-degree pulses in the proton channel. So that is what it is clear here. Here we are not applying. So here there is no effect of dipole-dipole interaction. But here what happened, we purposefully apply this 180-degree pulse to create dipole-dipole interaction, and this dipole-dipole interaction affect the echo. So we see the shadow or the radar fraction, like shadow fraction you evaluated, you can also calculate the radar fraction, and radar fraction can be evaluated as a function of time. And from this, you can get the dipole-dipole coupling constant. Just to read whatever is mentioned here, dipole-dipole coupling introduced in mass experiments by applying 180-degree pulses in the H1 channel. So this is the H1 channel. We apply 180-degree pulse and we create dipole-dipole interaction. Otherwise, dipole-dipole interaction is getting averaged out because of the spinning. So then you get the dipole-dipole coupling and you get the echo signal which is affected by this dipole-dipole coupling, and you can get information regarding the coupling constant. So technically they say dipole-dipole interaction cannot properly refocus the magnetization due to 180-degree pulses on H1. Correct? So this is the typical radar curve you get. You see a radar curve. And this has been called, we have recorded the radar experiment for 31 phosphorus and nitrogen 15. The coupling between 31 phosphorus and nitrogen 15 in this compound. This is a very common compound called diammonium hydrogen phosphate, called DAP. DAP is there. This DAP, what happened? The DAP is having nitrogen, correct? Na? And DAP is having proton, and DAP is also having phosphorus. So we have taken the average distance of nitrogen and phosphorus. Here nitrogen is an enriched sample because nitrogen 15 abundance is very small. We need to enrich, we need to increase isotope abundance of nitrogen 15 need to be enriched, and then we have to do the nitrogen 15 NMR, this radar experiment. And after doing radar experiment, as I mentioned, we get a scale factor. So you can calculate theoretically also, whatever the calculated this one, theoretically also you can calculate. And then you can match the whatever dot is nothing but the experimentally obtained. So you can theoretically also calculate and you can have a curve which match with the experimental value. And once the theoretical and the experimental matches, you get a scale factor. And that scale factor is nothing but the dipole-dipole coupling constant. And if you know the expression, you can say the nitrogen to proton distance is of the order of around 2.78 angstrom. Is this clear to you? This is the way we use radar, because radar can be very selectively used to, you can do a radar experiment with a different phosphorus, chemically different phosphorus and chemically different nitrogen. Selectively you can find out what is the distance between a particular phosphorus and particular nitrogen. Whereas by SADAR, there is a disadvantage of the SADAR is that only you can get the average picture. Hope things are clear to you. So dephasing time you are shown as a function of S by S0. So the application of pi pulse decreases the SADAR fraction, and that is why you get a decreasing signal, and by fitting the curves you will be able to generate the dipole-dipole coupling constant, and from that you will be able to get the distance between the nitrogen 15 and phosphorus 31. So these are some representative curves, so which I will not be discussing further. Now we will slightly move to a different topic. So this we have not mentioned any time during the last 11 lectures or the last 10 lectures. The reason being that I thought we will cover this forms a different category of NMR called a quadrupolar nuclear NMR. This NMR of quadrupolar nucleus is really challenging, recording NMR of quadrupolar nucleus. Why it is challenging? Because you can see from this slide, probably maybe in the first lecture I have introduced you this subject. The spherical nucleus you see here, nucleus positive charge, and then there is a distribution is more or less symmetrical. Whereas in the case of a quadrupolar nucleus, you see it is like a oblate. It can be a spherical, it's a non-spherical, it can be ellipsoid, correct na? And major and minor axis changes. So whenever there is a change in the shape from spherical geometry, we see a polarization of charge distribution inside the nucleus. Polarization of charge distribution inside the nucleus. And it is in fact affected also by the surrounding electron field, because why this charge nucleus will come? Because neutron we know, nucleus we know is considered only neutron and proton, is it not? So whereas neutron doesn't have any charge, whereas proton is having some positive, proton is having a positive charge. So why negative charge is coming? The negative charge is coming means we have an electric field gradient. There is a surrounding electric field. So that also creates some polarization. So this region will be more negative and this region will be more positive. So a polarization develops because nuclei will always sit in an electric field gradient only. Correct? No? Because we have got different coordination. We have got tetrahedral coordination, we have got octahedral, trigonal, or cubic coordination, 10 coordination, then we have 12 coordination. So as the coordination environment changes, the electric field gradient changes, and that will have a effect on the charge distributions at the nucleus. So whenever there is a charge in nucleus taking place now, then what happens? Something called the EQ. So EQ is nothing but electronic charge into Q is nothing but quadrupole moment comes. Quadrupole moment of the nucleus comes. That is called EQ. EQ will be depending upon the how the charge is oriented. EQ changes. That we will discuss it a little bit later. And there is something called the quadrupole coupling constant and all. Wait for some time. Probably today or tomorrow, next class, I will discuss what is this quadrupole coupling constant. So the main thing I want to convey this slide is that we have a non-uniform charge distribution, and this created some quadrupole effect in the NMR line shapes. This is a very important aspect because if you see the periodic table now, if you see the periodic table, around 70%, 65 to 70% is quadrupolar nucleus. Spin half is only 31. You see here, if you see all the elements, if you see, the spin half nucleus is only 31. Whereas in iron is quadrupolar nucleus only integer spin, like deuterium. Deuterium is having a spin of y, I is equal to 1. Integer spin. Whereas remaining 80% of the 80 nucleus or 80 spins has nuclear spin greater than half. In general, we call as a half integer nucleus, and they have spin greater than half. So the moment they have a spin greater than half means you have, as you see here, you have a positive charge, a negative charge, there's a polarization in the electron density. So this creates some sort of a coupling between this nucleus and the surrounding electric field. Let us move further. I thought this is an important aspect. I will explain to you this, then I will move further. I don't know whether you remember the chemical shift anisotropy. The first I have mentioned in the first few lectures, first 2-3 lectures or the fourth lecture or something, I have mentioned something called chemical shift anisotropy. What is chemical shift anisotropy? Chemical shift anisotropy is nothing but it's a vector of a vector. That is called a tensor. I don't know whether you have seen or not tensor. In laboratory frame, tensor is having 9 components. It can be represented by a 3x3 matrix. Huh? Okay, sure. I thought you will stop this further. Okay. So this part you may be knowing electric field gradient. So you must be remembering that we have got a tensor. Tensor can be represented. A second rank tensor can be always represented by 3x3 matrix, 3 rows, 3 columns. And in laboratory frame we have 9 components. And if you diagonalize it, when you are diagonalizing, when a laboratory frame get converted into principal axis frame, correct? Now PAS we say, principal axis system. Laboratory system get converted to principal axis system, then the 9 components which are shown here will get reduced to 3 components. So it will become only, we call it as a diagonalization of the matrix, and we have only got a diagonal components. That is what I have written here. In principal axis system, we have got only V1, V2, V3, or VXX, VY, and V33. And if you take an average of that, we get nothing but the isotropic electric field gradient tensor parameters. And there is something called asymmetry parameters. Like whatever we have mentioned for chemical shift it is sigma 11, sigma 22, sigma 33. So here it is V11, V22, and V33. So if you take the ratio of V11 minus V22 by V33, because always the V33 is nothing but VZZ. Let me clarify you, V11 is nothing but VXX, and V22 is nothing but VYY, and V33 is nothing but VZZ. So always V33 must be greater. So V1 minus V2, it can be eta can be minus also, it can be plus also. V1 minus V2 to V11 minus V22 divided by V33 is a parameter called asymmetric parameter. So this asymmetric parameter, if it is 0, then we call axially symmetric system. So this we have also discussed in terms of the chemical shift anisotropy. So if you correlate that aspect with this aspect, it is very easy to understand. The EFG means electric field gradient. If electric field gradient is 0, we call it an axially symmetric system. So as the function of eta, if the eta increases, then we say it cannot be more than 1. So as a function of, because V33 always is the highest value, V1 and V2 are lower than that only. So EFG can be used as a parameter to understand the symmetric environment around this one. Let us, I think maybe I will stop with this slide. So the important parameter you get in quadrupole NMR is nothing but the quadrupole coupling constant. So from the CQ, which is nothing but the quadrupole coupling constant, you can say what is the local environment around the quadrupole nucleus. For example, if you have a highly symmetric system, then CQ will be in kilohertz or in hertz. If you have a highly asymmetric system, the asymmetric environment will be very high, the CQ value will be in megahertz. So CQ is a parameter which can decide the coupling, the local environment. CQ varies with the local environment, and it is given by this expression. What is Q? Q is the charge of the nucleus. Capital Q is charge of the nucleus, and small q is the charge of the electric field gradient, and E is nothing but the electronic charge. And gamma is a parameter called Stern-Hamer anti-shielding factor. So that is created by the distortion of core electrons. Probably we will discuss this in the next session in detail, how to calculate CQ and how that CQ parameter can be utilized for getting different informations in solids. Probably this I will express in the next class because there is some angular term involved in the second and first order. So this we will discuss in the next class. And please feel free to ask any questions, and also mail me or telephone me, and please try to finish the assignment. Today is my 11th class, next tomorrow is my 12th class. In fact, we can discuss something. If you are having some doubts or if you have any clarification, please write it down. Next class, which is on Monday at 3:30, we can discuss at length. So if you have a lot of questions, and it will be better, I will discuss on whatever I taught only. Now, otherwise, I will talk something more. If you have any queries, then I will discuss on that only first. So I will also summarize something which I have told previously. So not much portions I will be taking, but you come with some problems or come with clarifications, we can discuss it in length. So try to do the assignments, maybe submit sometime next week. So with this, I conclude. Please, if you have any questions, please rise. Can we see any questions? Please ask any questions. Any question? 4 people are there, na? YouTube, how many were there? 3?
Total 6.
Total 6. 6 people will come.
Mostly 6 people.
That's it.
No question, I suppose.
Any questions, please? Or mail me. We can discuss tomorrow. Next class also Monday. We can discuss it then. Please feel free to ask any questions. Any clarifications?
Okay, no question then.
Yeah, if there are no questions, I will conclude. So thank you very much for coming and attending. So we will meet on Monday now, Monday 3:30. So, okay. Thank you very much.